Hello everyone. In the previous class we have discussed about BJT fabrication. So in today's class we shall discuss the coupled diode model. A coupled diode model is also referred to as Ebers-Moll equation. So as you can see from the figure, a PNP transistor, a PNP junction with a emitter, base and collector terminals. So from the simplified PNP transistor shown in figure, the delta PE represents the excess hole concentration at the edge of the emitter depletion region. So as you can see, the white color shade, the delta PE, so that represents the excess hole concentration at the edge of the emitter depletion region. Also it is shown that delta PC, so other side, the delta PC that represents the hole concentration at the edge of the emitter region. And WB is the width of the depletion region. So the equation for delta PE and delta PC can be written as delta PE is equal to Pn into e to the power q VEB by kT minus 1, and delta PC equal to Pn into e to the power q VCB by kT minus 1. So we have seen all the currents, that is IB, IC and IE, that is emitter current, base current and collector current, and we now understand how to relate them in a ratios. We also know the terminal currents. Until now we have mostly assumed emitter base a strong forward and base collector a strong reverse. Let us develop the coupled diode model. So this topic is a coupled diode model for a BJT that can be biased in more than one way. So there are many models, but we will do only one, that is a coupled diode model. So why it is called as coupled diode? Because we can solve the case for PN and NP diode separately here. So we can, so in a diode, as we know, we have a PN junction. So because we can solve the case for PN and NP diode separately and add the solution to get the simple circuit model for PNP BJT. So here diode 1 and diode 2 are coupled, so that diagram will be shown later. So here diode and current source are used, two diodes and two current source are used, and diode 1 and diode 2 are coupled in a common circuit point. First let us look at the base region under some conditions we have not yet considered until now, and define some new terms. First note that the solutions for emitter base and collector base hole injection can be linearly superimposed on each other. And also note that voltage and depletion region in the diagram. So here in this figure there are two modes, normal mode and inverted mode. Normal mode it represented as N, and inverted mode represented as I. So subscript N region is normal mode and I is a inverted mode, and the middle figure is a superposition of those two. So with respect to first figure number 1 in the slide, here the BJT in normal forward active mode. So BJT is normal forward active mode. That is emitter base is forward biased. As you can see here, the emitter P plus, it is heavily doped. VEB, that is voltage across the PN junction. VEB, P is positive, forward biased, P is positive and N is negative. So emitter base is forward biased. Similarly, collector base is reverse biased. If you look at a hole concentration, observe the graph. If you look at the hole concentration, the base, the excess delta PE, hole concentration across the base, the excess hole concentration, that is delta PE, at the edge of the emitter depletion region, and WB is the concentration that goes to 0. So delta PE is at the higher level and WB is 0. So that is edge of the depletion region, where all the holes are swept across to the other side here. And delta PE is dependent on the emitter base voltage VEB. Now look at the figure number 3, that is inverted mode. So there is also solution for doing this thing backward here. That is, so in this case, collector base is forward biased. Observe there, the collector P is forward biased and N is reverse biased. So collector base is forward biased, that is positive voltage on the P side and negative voltage on the N side. So collector is doing emitting here. So see here, collector is doing emitting, and now reverse biased emitter base junction. So observe there, reverse biased emitter base junction, that is P is negative and N is positive. So it is reverse biased. So look at the hole concentration across the base now. So observe the figure, that is graph. There is hole concentration of the base on the WB side. So on the WB side it is higher. That's why here I am injecting the holes, because collector becomes emitter here, it is injecting the holes. If you see, if you call the delta PC, meaning is excess on the collector side of the on the base. Delta PC represents the hole concentration, excess hole concentration here at the collector side. Emitter base is reverse biased here. Emitter, that is P plus, is connected with the negative of the battery and N is connected with the positive of the battery. So emitter base is reverse biased. So zero concentration here. So delta PC is similar to delta PE, only the difference is dependent on the collector base voltage. Now the second figure, that is middle one. So this is, if I forward here, in this case both are forward biased here, both the junctions PN as well as NP, both are forward biased. So if I forward biased both emitter base and collector base, I can add the two solutions by superposition and get one solution. So that is the figure. By adding the first one and the third one, we get the second one, that is the superposition of the two solutions. So for the symmetric transistor, these various components are described by defining A is equal to Q AdP by LP, hyperbolic function of a hyperbolic trigonometric function cot H, WB by LP, and B is equal to QA dP by LP, hyperbolic cos function of WB LP. We have IEN is equal to A into delta PE and ICN, there is B into delta PE with PC is equal to 0, and here N, subscript N refers to the normal mode, and IEI is equal to minus B delta PC and ICI is equal to minus A into delta PC with delta PE is equal to 0. Here negative sign is because it is in the inverting mode. The subscript I refers to the inverting mode. So we are showing the current direction same, but it is the hole is moving from the other side, collector to the emitter side. So the negative sign. The emitter and collector current can be written as, here the emitter and collector current can be written as IE is equal to IEN plus IEI, that is emitter current in the normal mode and the emitter current in the inverted mode. The sum of these two is nothing but A into delta PE minus B into delta PC. So that is equal to capital A into e to the power QVEB by KT minus 1 minus B into e to the power QVCB by KT minus 1. So this is the equation for the emitter current IE. Then collector current IC is the sum of the current collector current in the normal mode and the inverted mode, that is ICN plus ICI. So that is equal to B into delta P minus A into delta PC. So that is equal to B into e to the power QVB by KT minus 1 minus capital A into e to the power QVCB by KT minus 1, where capital A is nothing but it is A into Pn and capital B is nothing but it is B into Pn. So we can see from the equation that a linear superposition of the normal and inverted components that gives the result that we have derived previously for the symmetric transistor. So it is the superposition of the two normal mode, normal and inverted components. So it is possible to relate the four components of the current by factors for symmetric transistor by considering reverse saturation current. For example, the emitter current in the normal mode can be written as, so as you can see in the slide, IEN is equal to IES into e to the power QVB by KT minus 1, where delta PC equal to 0, where IES is the magnitude of the emitter saturation current in the normal mode. Since we specify delta PC equal to 0, in the delta PC equal to 0 in this mode, we imply that VCB equal to 0. Therefore, we shall consider IES to be magnitude of the emitter saturation current with the collector injection short circuited. Similarly, the collector current in the inverted mode is ICI. Collector current in the inverted mode is represented as ICI. So ICI equal to minus ICS into e to the power Q VCB here. Instead of VEB, it is VCB divided by KT minus 1, where delta P equal to 0 here. Here the ICS is the magnitude of the collector saturation current with VEB equal to 0. So as before, the minus sign associated with the ICI, the meaning of that one is the inverted mode. In the inverted mode, the holes are injected opposite to the defined direction of IC. So normally we define the IC current. So but In the inverted mode, the holes are injected opposite to the defined direction of the collector current. That's why the negative sign. So the corresponding collector current for each mode of operation can be written by defining a nu for each case. So that is ICN equal to alpha n into IEN. That is equal to alpha n into, substitute the equation for IEN, that is IES into e to the power QVB by KT minus 1. Similarly, IEI equal to alpha I into ICI. So that is equal to minus alpha I into ICS into e to the power QVCB by KT minus 1, where alpha n and alpha I are the ratios of collected current to the injected current in each mode. We notice that in the inverted mode, the injected current is ICI and the collected current is IEI. So notice that here the injected current is ICI and the collected current is IEI. Now the total current can again be obtained by superposition of the two components. So that is IE is equal to IEN plus IEI. Now substitute the values. That is equal to IEN is nothing but IES into e to the power QV by KT minus 1, and IEI is nothing but it is minus alpha I ICS into e to the power QVCB by KT minus 1. Similarly, IC equal to ICN plus ICI. So ICN is equal to alpha n into IES into e to the power QVB by KT minus 1, and ICI is equal to minus ICS into e to the power QVCE by KT minus 1. So these relations were derived by the scientist called as J.J. Ebers and J.L. Moll. Therefore, they are referred to as the Ebers-Moll equations. So these are the Ebers-Moll equations, IE and IC. And also we have alpha n IES equal to alpha I ICS. N suffix n is a normal mode and suffix I is a inverted mode. For both symmetrical and non-symmetrical transistor, the Ebers-Moll equation can be written as IE is equal to IES into delta PE by PN minus alpha 1 ICS into delta PC by PN. Similarly, IC equal to alpha n IES into delta PE by PN minus ICS delta PC by PN. So that is equal to ICS by PN into alpha I into delta PE minus delta PC. So here the equivalent circuit for both equation can be written as you can see from the figure. So this is the coupled diode model. So here the two diodes, one in emitter base junction and another one is at the base collector base junction. So diode and a current source and another diode at a current source. Diode 1 and 2 are coupled in a common circuit point, that is base. So this is a coupled diode model, and the various currents, that is IE and IC, the direction of the current is shown. Also the current source are shown here. So here IB is equal to 1 minus alpha n IES into delta PE by PN plus 1 minus alpha I into ICS delta PC by PN. Total emitter and collector current can be represented in terms of saturation current as IC equal to alpha N IE minus 1 minus alpha N into alpha I into ICS into e to the power q VCB by KT minus 1, and IE is equal to alpha I into IC plus 1 minus alpha N into alpha I into IES into e to the power q VEB by KT minus 1. So the terms 1 minus alpha N and alpha I into ICS and 1 minus alpha N and alpha I IES can be abbreviated as ICO and IEO respectively, where ICO is the magnitude of the collector saturation current with emitter junction open, that is IE equal to 0, and IEO is the magnitude of the emitter saturation current with collector open. So the Ebers mole equation then becomes IE is equal to alpha I IC plus IEO into e to the power q VEB by KT minus 1, and IC equal to alpha N IE minus ICO into e to the power q VCB by KT minus 1. So the equivalent circuit shown here in the figure. In this form, the equations described both the emitter and collector current in terms of a simple diode characteristics with a current generator proportional to the other current. So the resulting current characteristics of the transistor appears as a series of reverse biased diode curves displaced by increment proportion to the emitter current. So that is shown in the figure 2. It shows the collector characteristics with normal biasing. So the first figure is the equivalent circuit of the transistor, and the second one is the collector characteristics with normal biasing. So the equivalent circuit, so in this form the equations describe both the emitter and collector currents in terms of a simple diode characteristics with a current generator proportional to the other current. So which results into current characteristics of the transistor, which appears as a series of reverse biased diode curves displayed by the incremental proportional to the emitter current. Thank you for watching the video.